Hello everyone, and hello hello everyone. My name was Gyaneshwar, and our teammates Satvik and Mahesh, and and our project was title was flower species classification using transfer learning and web development, and this we use Oxford 102 dataset for our app, and we've wrapped up using web development app for mm, non-technical user specifically. And our outline was here. The outline for today, I will start with some background and the problem we are trying to solve, then review related work. Next, we will walk in through our method and system design, how experimental results show experimental results, and give a short demo of the web application, and end with the conclusion and our future works, like what we're gonna do in the future. And for the next one, the background and motivation that we do have with the project was uh, accurate flower identification is important in the area, in area like biodiversity monitoring, agriculture and education purpose. Traditionally we need a human expert to look over the plants, and which doesn't scale well when you have thousands of photos and want a phone app with the work in a real time. At the same time, deep conventional neural network with the transfer leaving have become very strong for image recognition. Our motivation was to combine these ideas and build a accessible flavor recognition system that everyone can use through a simple interface, and without human expert you can do by yourself. And problem definition and objectives for this project was formally our problem is given in a single RGB image of a flavor, predict which species it belongs to. We as we discussed, we use the Oxford 102 dataset, which has 8,189 images across one or two species, with a large variation in a pore scale and lightning. And we defined two main objectives. All the images we defined into two main objectives, and which was high accuracy classified using transfer learning with a DenseNet 161, and second, delivered a complete end-to-end system developed as a Flask web app and REST API for non-technical users, good user-friendly interface, and attractive interface, which using CSS and HTML, all the stuff in the Flask web app, and reset API for non-technical users mostly. And next, coming to literature review was it was Oxford Flavor 102 dataset by Nils Black is a standard benchmark for fine gardened flavor recognition. Early approaches use handcrafted features such as shift descriptions combiner with the SVM classifier. These approaches struggle with the dataset challenges. Many classes looks very similar, and they have very variations in a scale, ports and illumination. The motivation that move forward deep learning based methods. Now the updated method was deep learning based method, which was the deep learning and neural learning was analyze images thoroughly and accurately, and which coming with the deep learning CNN architecture like VGG, ResNet and interception becomes the standard for image classification. Transfer learning is now the default strategy. Start from a network pre-trained on ImageNet and fine-tuning in on the target domain with less labeled data. DenseNet, which we use, is densely connected CNN that refuse features and help gardeners flow better through the network. And the literature mostly focus on accuracy number related to relatively few paper talks about real development and user friendly interface. And our contributor is combined strong accuracy and production stylish and web page and user friendly interface for which we mentioned mainly targeted non-technical users with the interface and user friendliness. And next, coming to method data sets and explanatory data analytics, EDA, which we call shortly. We follow the predefined training, variation and test splits of Oxford Flavor 102. Each of the 102 classes is represented in all three splits, and our class distribution plots show no extreme imbalance. We also computed pre-channel RGB statistics. We also like channel pre-start mean pixel per channel and mean pixel per channel, and it was imbalanced. And we RGB statistics means mean, standard and deviation and like histogram, and we determine on these four categories. And the red channel trends is to be slightly brighter and the blue darker, and which influence our choice of normalization parameters. And you can see like RGB colors, we use RGB colors to determine all the stuff and all the variations between like mean, standard and deviations and histograms. And coming to method pre-processing and data augmentation, for pre-processing, each unit image is resized so that the shorter side is 255 pixel and then cropped to 224 into 224 pixel. Value are scaled to zeros and ones, are normalized using like channel wise means and standard deviation estimated from the train set. During training, we use like data augmentation, random rotation, horizontal flips and like random resized crops to improve generalization, and that's how it works with the methods. And coming to model architecture, like our model is, which we mentioned, like DenseNet 161 with the ImageNet pre-trained weights. In a DenseNet, each layer receives future maps from all the previous layers, which encourages future rescue and help coordinates. We replace the final classification layer with the custom head, a fully connected layer from the 2208 futures to 1000 units. ReLU dropout with a probability of 0.25 and final fully connected layer to 102 outputs, followed by long softmax. And these are like architecture which we use in this project. And coming to method and training setup, training is implemented in PyTorch. We use native log like hood loss and Adam optimizer with a running rate of 0.003, and the batch size is 64, and we train for roughly 5 approaches, which gave a good trade-off between performance and training time of our hardware. At each approach, we record training loss, variation loss, and validation top 1 accuracy. After training, we select the model with the best variation accuracy and the evaluation of the model. So we selected using like most of the time we like taken like which has like high accuracy and evaluation, and that's how it works with the accuracy. And coming to a method, web system and a workflow. Our workflow, like to turn the model into something people can actually use, we built a Flask web application with HTML template and CSS, custom CSS to get like a user friendly and like get better experience for the users and like get like easily understand for the users. The backend loads the trained DenseNet model once at startup, handles files, uploads and applies the same pre-processing pipeline during the training, and runs interface to get top K prediction. The system explores several routes, like for the home, overview and performance plot, and for the predict, where users upload an image and result, which shows the image plus the predicted species and probability about which explain the dataset and model. Like the diagram on the side summarize the data flow of user upload to a prediction, like the flow, like when the user upload a picture to the prediction, what goes on, like the workflow is on the diagram, which was like simplified on the right left side of the PPT. And quantitative evaluation. Coming to evaluation part, here we show our results over the training approaches. Both training and validation loss decrease steadily and validation accuracy rises. then stabilizes. Our best model achieves like 92.29% top 1 accuracy on the validation set and 91.82% on the test set. Give the it is one or two classes fine. Granted problem which mainly visible similar species, this number indicates the densenet 161 with the transfer learning performance very strongly. And coming to our result part, result example which was we got like to better understand the model behavior, so we also looked into qualitative examples. On the left side we shown, on the right side we shown good cases, flavor that are clearly visible with the typical colors and clear background. For these the model predicts the correct species with the higher confidence. On the right we have highlight more challenging cases, images which cluster background, usually lightning, partial view of the flavor and or the species that looks nearly identical. Even in many of these harder examples, the correct label still appears with the top K prediction, which is useful if we present multiple suggestions to the users. And coming to a demo I'm gonna quickly go into our website and we're gonna look our demo. So, and this is our our code and all the stuff, our input and all. So this is our code. Yeah, this is our code, and I don't want to go through into the code because it was like 15 minutes take time. So this is our interface, like very user friendly, and it was like highly integrated with like our team was done very good with the interface. And going into classify flavor, and here is you have like an slot to upload an image. Let's choose image. It redirects you to your file manager, and you like I set up the flavors over here. Like you can grab one flavor, like select one flavor and upload an image and like hit on identify flavor, and here is the flavor, and like it was matches with orange Danalia like 54.5%, and it was like English marigold, it was matches with like 21.29%, and it shows like orange Denali like most match it was like 54.5%. It was high accuracy, like high probability with the matching of the orange Denali, so that it was matches with orange Denali. And this is how it works, and this is how it shows, and this is our like web application and web page. And going back to the demo, okay, and going back to our conclusion, to summarize, we built a complete pipeline for a flavor species classification using DenserNet 161 and transfer learning of Oxford flavors 102 species. Like the 102 determine like it has like 102 species on the data set. Our model reaches like about 92% validation accuracy and 91.8% test accuracy. EDA helps us choose normalization and confirm that the dataset splits were responsibly balanced. Finally, we deployed the model in a Flask web app and REST API, turning a research model into an interactive tool that could be useful for education or a citizen science. And coming to our our plan for the future work was like these are the main reference we built on, like the Oxford Flavor 102 datasets paper, work on a transfer learning and DenseNet and a PyTorch library, and we use IEEE style for all the citations and and IEEE citations we use for the model. And the several directions of our future work was like one of the extended systems to cover more plant datasets and additional species, and another is to explore lighter backbones such as MobileNet and the optimizer for the models. And these are our reference papers, and we mainly built on like Oxford 102 datasets paper, and we use like we use like transfer learning, DenserNet and PyTorch library and some other references from